So next one is Schottky barrier CNTFET. So Schottky barrier, you have a tunneling of electrons and holes from potential barrier constituting the current. So Schottky barrier, it is going to be a metal semiconductor. It is just like your MESFET. You don't have the oxide layer. It is going to be metal semiconductor layer. So I'm going to apply the gate voltage, and that gate voltage is going to control the current as well as the barrier width. So the construction is shown here. You see here, you have a gate, you have on a silicon substrate, you have a directly you fabricate your source and drain, and in the gate you will be having gate dielectric carbon nanotube, again dielectric and silicon. So usually gate dielectric CNT you have, but here you see the CNT is placed inside between the source and drain in a symmetric way. Above and below the CNT you have a dielectric SiO2 layer, and above the topmost layer you are going to have your gate region. You are going to have your gate terminal. Okay, this is the construction of Schottky barrier. So you have a Schottky barrier carbon nanotube FET, which is seen here, and this is the band diagram you can see. So at the Schottky barrier, you have a metal contact. So this is metal semiconductor junction. I told you oxide is not MESFET. It is going to be a metal semiconductor junction. So this is metal, this is semiconductor. This is metal, this is semiconductor. And here you have metal, oxide, semiconductor. So you have both MOSFET and MESFET here. Okay, in the source and drain terminals you have metal semiconductor junction, whereas other in the gate you have the metal oxide semiconductor terminals. Okay, the construction, the device is made up of intrinsic or lightly doped p-type silicon which form the substrate of the device. Okay, the CNTFET is formed by one or more CNTs perfectly aligned in position under the gate section. See, ultimately our aim is the channel should be completely made up of CNT. But one problem is when you have silicon based FET, the problem is fabrication is the advantage is fabrication is very easy because I just need to grow silicon layer in between the source and drain. But when you are going to use carbon nanotube in the channel, you have to going to fill your complete channel by carbon nanotube. Then you have to position the carbon nanotubes in a perfect way. So the positioning, the alignment, all will take a lot of time, and you have to do it with a very high precise activity. Otherwise the device will not, after fabrication the device will not work. You have to start again from the beginning. So whenever you are going to use carbon nanotubes, see here, so the CNT should be perfectly aligned and well positioned. The gate, everything should be happen properly. Otherwise chances that the device may not work properly. So electrons see a tunneling barrier in the on state, and gate electrostatics will control the barrier. So whenever you are going to apply the gate voltage, that is going to control the flow of current, and when the device is going to be in on state, you have to supply voltage more than threshold voltage. The device will be in on state, and the device in the on state, the drain current is going to be controlled by VGS. That is what in the last point you see. Since the current carrying mechanism is tunneling, the on current is limited. So this is the VI characteristics for MOS and Schottky barrier FET. They are shown here. MOS type FETs have low off current compared to Schottky barrier type. So even in the off state, the current will be almost constant for a Schottky barrier CNTFET. So you can see in MOSFET at the off state, the current is very minimum and it increases slowly. Device is turned. This is your off state and this is your on state. And in Schottky barrier, you see even in on state, the current what you see here is going to be very, very larger. So that's what they say. MOS type CNT have a low off current compared to Schottky barrier type carbon nanotube FET. So this is the VI characteristics, and so you can see the VGS is going to control the ID. As you increase VGS in positive sense, the drain current will increase. As you decrease VGS, as the VGS becomes more and more negative, the drain current is very, very small for MOS CNTFET, but it reduces very, very gradually for Schottky barrier CNTFET. So that is what is the conclusion from this VI characteristics of MOS CNTFET and Schottky barrier CNTFET.